Hello, everyone. Good morning. Good afternoon. Welcome. Welcome to the stream. We are going to work on a continuation of what happened last week. Namely, this issue, which is extending the Go runtime with facility to help CockroachDB manage CPU usage and memory better. And so we started last week by defining a notion of task group inside the Go runtime, which doesn't exist today, and adding an API in the Go runtime to manage those task groups. And today we are going to try and demonstrate this works by actually using it inside CockroachDB. And so what we have here is the code we wrote last time that is able to attach a task group to the current Go routine, and then a prototype API to retrieve the scheduling ticks for the current task group separately from the moment where it was incurred. And inside the scheduler, we have here this increment of the scheduling ticks. Now, after this was done, I did some research to think about this, how this would be used in particular inside CockroachDB. And so I realized that the inspection of the CPU usage via the scheduling ticks is going to happen asynchronously. So last time we had this API that is going to manage the task group only from the current Go routine, and therefore had this kind of assumption that we were able to access this asynchronously from multiple Go routines. That was actually wrong, because if multiple Go routines are running on separate CPUs, they might actually be sharing the same task group and the same scheduling tick counter, and therefore this increment here should be atomic. And the extraction of the value here, probably we want that to be able to be available separately in a separate Go routine. And so having the API retrieve the scheduling ticks from the current Go task group is not exactly the best API, is the best way to inspect this value. So we need to do two things. First of all, we need to change this code so that it is race free, so that this is not going to be a problem when we have parallelism. And the second step is to introduce an API that can inspect a task group separately from a different Go routine, and then also make that race free. So we're going to use atomics. So first step, let's do this. So there are atomic built-ins already in the Go internal atomic package. So let's see what we have here. We want an increment, atomic increment. So that would be add, probably. Is there an add somewhere? X adds. Probably. Let's see how this is implemented. X add. Exclusive add. Yeah, I think that's good enough. That's what we need. Yeah. And it returns the value after the increment. All right, that works for us. Let's see. So it's going to be a +1, and get ticks is going to be atomic. And so we probably need this and a1, right? Let's verify the API. Oh, it's uint 32, 64. Probably want a 64 here. All right, 64. Off we go. And now here we had an API that's given a task group is able to retrieve some information about this, but we made a mistaken assumption last time, which is that the task group structs would be only accessed from one coroutine, and that's completely mistaken, of course, right? And so we are going to extend this by having the task group return an empty interface, and actually returns the task group here. TG, return TG. Off we go. And then get gas reset ticks for all Go routines in the given task group. So we are going to have a type task group, and that's empty interface task group. All right. And now we are going to have... Oh, we don't need the empty interface. We actually can say task group like this. Like this. And then we can say task group. And then we cast it. Task group dot t. Thank you. We know that's a valid cast because there's only one way to get such a thing, and that is from set task group. It's not an interface. I don't care. Oh, it's not. Oh, yes. That's not how a cast works. This is the way it works. There we go. And then we say return atomic load. How many loads? Load 64 probably, yeah? I apologize in advance. There is a package delivery coming my way between now and the end of the stream. I'm not controlling the time, and I'm actually hearing a truck right now. I might need to leave the stream momentarily. Yes, that's exactly what it is. I'll be back in a minute. All right, we are back on stream. Thank you for bearing with me. This package, I will share on stream at some point a bit more, is a dance pad. I am an avid fan of Dance Dance Revolution, and for the longest time I was very sad because all the equipment that was available online to play the game was very poor quality and did not resist my assault. And I only learned last month of a company in Poland who is making affordable, new hard dense path. And so I ordered one, was just delivered. And so I will probably work on that a little bit at the end of the day. We'll see. Anyway, let's come back to the task groups. And we need here to import this. Internal atomic. And we are going to explain this. Presents a collection of coroutines. All right. And I think we are all right with this. Let's build this to verify that it builds properly. Build all. I don't remember which command we used. No. Let's see. Make.bash. It looks like it. Yeah. Yes, I made a mistake. Say package is called runtime internal. Cool. All right. So we got our build toolchain that is able to set task groups and get task group scheduling ticks. We could add more, but I think we do already have the other notion of task group ID, coroutine group. Yeah, I kind of expect that this, yeah, that is also complete. That doesn't seem, yeah, that's actually probably fine. All right. Yeah. So what I'm thinking about is that we'll probably want to have something like a label to identify those task groups. And so the question will be, how do we do that? Well, we'll see in some time. All right, so we have here a little of a challenge, which is that we don't have one Go routine per query in CockroachDB SQL. We have a main Go routine for the entire SQL session. And so, oh, but that might be actually okay. Oh. Okay, let's change a little bit the definition of the work. Let's do CPU usage per session, per SQL session, so that we can measure the SQL usage of different SQL sessions. Sorry, the CPU usage of different SQL sessions side by side. And if later we want to do it more fine-grained, then we can work on that. Anyway, so we have here a Go runtime that is customized with a Go compiler that is customized. And so this is now in this directory. Now, if we want to use it to build CockroachDB, we need to set the environment variable Go root, I think. Right? Yeah, so that's the one I have today. And that's the one I'm going to set now. And then if I say which Go, I get this one, because I think that my path has a regular US or local at the end. And so I'm going to say for path is go root / bin send path. And now my Go command is customized. All right. Now we're one step further. And what am I going to do from here? We're going to do two things. First of all, we're going to create one task group per SQL session in CockroachDB. All right, so how do we do this? We need to come back to our directory tree for CockroachDB. I think that is this one. Well, no, it's okay. PG, I think, I don't know where there's defined. And I think it's a server package. Yeah. Server.go. PGL, that's a Postgres network listener. And there will be an accept. An accept call to accept the connection and actually start it. And where is that defined? Here. So where is this? Where is this used? In pre-start, maybe. Am I in the right function? Yeah, looks like it. What does this do? PGL. Okay, let's see where this is being used. Here, start serve SQL, accept client. We're closer, we're getting warmer. All right, serve cons, that sounds good. Con manager, serve width. Yes, here we are. So serve width is a function that will spawn a Go routine for every incoming connection. And that means that here we can keep track of a task group. We can define a task group for the entire Go routine for that connection, and then try to get data out of this. So suppose we were to create a task group for those connections. So like what we're doing here is runtime.setTaskGroup. And now we are using our custom Go runtime. This should build without errors. Yeah, it's a custom version, doesn't really have a version. So let's ignore the Go version and see if this accepts to build our code with the customization. Going to be surprised. Seems to build so far. Still no errors. Need to add a little bit of music. This music is from the C418 album Minecraft beta. So as you can see, the runtime.setTaskGroup call has been accepted. Even though my editor is confused because my editor doesn't know about my custom Go build. My shell here knows because we configured the Go root here and the Go and the path. So this is now available. Now set task group will set the task group for the entire tree of Go routines from that point. But if you want to inspect all the CPU usages, that means that we need to create some separate facility to inspect all the task groups that have been recognized. And now here we have a little bit of a challenge. Oh, hi, easy with the thing. Hello. So we have here a little bit of a challenge, which is that we need to keep track of those task groups. But we also need to be a bit careful, because at the end, when the connection goes away, we do need to get rid of the task group in our collection so that it can be garbage collected properly. As you remember from the other piece of code that we wrote, we allocate here on the heap a task group when this is defined. So when this is collected, eventually we will need to ensure the garbage collector can take our task groups away. And so what we want here is to keep track of task group and then remember it. And so we have probably a task group collection. And then we will have a defer. like this. That defer will run when the servcon call terminates. And what is the task group collection? We will need to define this. And so how do we do this? Well, we probably want that to be defined per server. Do we want that per SQL server, or is that something that we define for the server? Well, where do we want the API to inspect this? Do we want the API to be visible within SQL, or do we want that to be visible outside of SQL via an HTTP API? I suppose I don't really have an opinion about this, and so I think that we are going to define this in SQL for now. And the reason is that I think that we can make a case of extending the show sessions mechanism with this. Oh, show sessions. Oh, show sessions is doing this by session ID. Oh, okay, so that's maybe not the right place to do this. Where are the sessions being? All right, so we want to associate this with SQL sessions. And SQL sessions already have a collection of all SQL sessions. So there is in SQL session cancel sessions. I think that's where we need to have a look here. So SQL status server. All right, that's what we need. There is a SQL status server. Interesting. Okay, that facility is kind of odd. It's odd. That's not the place I need to look at, probably. Session data. No. Where is the cancel session stuff defined? Let's see. Let's look for it. Oh, we have a CRDB internal table. Yeah. Node sessions. It's here. Oh, list local session. Oh, it goes through the RPC server. Oh my. We need to file an issue about this. So status server is defined. Yeah, okay, so there is a design fault here going on. Like that's something that happens sometimes when you do an investigative research. And that is improper dependency on the RPC servers from SQL. This came up while reviewing. So here I'm going to quote another PR that I was reviewing earlier. And also investigating, and now we're going to report this. So what was this pull request? It's from Jordan. What is this one? Oops. There are multiple places in the SQL code where say is an abstraction inversion. The SQL code calls into RPC endpoints, which in the server package, which are not intended for use directly by SQL. In particular, these RPC endpoints are not yet defined for SQL-only servers, which occur in multi-tenant deployments. The proper way forward is to define a separate subservice API inside the SQL package, which depends only on, say, client-side KV API and not dependent on the server machinery. and also is guaranteed to be available in SQL only pods. Okay, so systems affected. SQL list of sessions and queries and cancellation. And the other things that Jordan was looking into here was KV level table size on disk. All right. And who is the other person who is likely to, well, let's talk about this Jordan only for the time being. And that is a bug indeed. Yeah, all right. So where is this defined in the server package then? Cancel. Cancel. Oh, it's not here. Cancel session. All right. And then there is a session registry. Aha. All right. So that's what we wanted. All right. So there is a cluster-wide session ID. And then we have a entry for the registry session. And so we likely have a registration of new sessions somewhere elsewhere in the SQL code to add a session that is being added. So where are those sessions? Registry. Where is this defined here? New session register. All right, that's what we need. All right, where is this called? What are we working on? So the question is always answered by a link to today's CockroachDB issue, which is pointing to this issue here. And so what we really want to do is to enhance the Go runtime to help CockroachDB manage CPU and memory usage better. So here it is. Register. Oh, that is nice. All right. X. Oh, so that's why it's an interface. Oh, I will accept this. Cancel query, cancel session, serialize. Interesting. Yeah. I suppose. Yeah, so we actually want to associate our task group to this. So where is this run call being made? Probably from the pgwire package. Here and here. Oh, fascinating. Oh. Oh, that is good. So an internal executor is running in a separate Go routine. Oh, that is good. I like this. And serve con. Very good. Very good. And a deregister. Okay. Now we're back in business. All right. So this is in this run function that we want to define our task group, not in the server. So let's remove that code here because that's not what we want. Run dot whatever. What did we have? That needs to go in the other file here. And we are going to define our task group in the executor. All right, I like this. X.task group is runtime.set task group. And we don't need this anymore because that is going to be automatically deregistered at the end. All right, and now we are back in business. And the next step from here is to make it possible to retrieve the task group from a session. So what is the registry session here? All right, which is better. And then status here, how does this work? Session registry, find session. What is serialize all? My gosh. Oh, this is so messy. This design, oh my. So not happy about this. This makes no sense. Yeah? Yes? Okay, actually I'm not too unhappy about this. Right, session. And then we are going to add a field here. Come on. Say number of scheduling ticks for all go routine marked associate to that session. All right. So fix me. Collects this across all nodes upon query termination. Currently executing queries on behalf of the session. It's away. Yeah, let's copy paste this comment here. We should actually file an issue about this because it's pretty clear that this was not properly defined, and so we actually need to report an issue about this. All right. Status pb.session not go properly. Memory usage across all nodes. The fields and in status.proto session, so sorry. Are currently populated only from monitor data on the gateway node. When queries are distributed, they incorrectly miss out on memory usage incurred on other nodes. Arguably, the fields are not properly defined. Instead of single fields, we should have an array, one for every node. or some similar interface which enables the client to distinguish which node was incurred, which memory usage. Off we go. And so the two people who are looking at this right now are this, and so the name is going to be queries. Not yet. Okay. Observability. Memory usage. There we go. Alright. I'm going to file this as a link here. And the new one is a uint64 text. Let's call this experimental. All right. Now we have our field in the session, and now we are going to do serialize all. Serialize. We're looking at a func-serialize that is lowercase, and probably it's here. There we go. So we have here. So what was this API we created? Oh, it's in task group.ip get task group getDix. Comma. All right, let's build this. Yeah, I'm not in the right directory anymore. All right, so that gives us a server pb.session. I need to import the runtime package. And I need to define, yes, a task group field in the con executor struct, which is here. Is go runtime task for this executors go routine and show. All right. Oops. Do I have everything included? Yeah, it looks like it. All right, so that built. So now we have the session data, and let's see now if we can make it visible through SQL. List local sessions, and that gives us a list session response. And what does that contain? An array of sessions. So yes, now we have the data available here. Amazing. And so we are going to add a field here. Session schema pattern. All right. And that's going to be getDix. going to be int. All right. And then we have it here. All right. And now let's try to build this. Cool. Now we're in business. Cool, 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 cool. Let's start a server with this. Oh, I want a different shell. Thank you. Start single node. Access. SQL. Access. Show sessions. Oh yeah, show session. Okay. There we go. Skeptics is 0. That is not great. It's supposed to be more than this. Shouldn't be 0 since our go routine is being scheduled. Let's try this. Has not been increased. All right. Well, now there's something wrong, which is probably that our scheduling ticks are not getting populated everywhere. All right. So we are going to take a small break. I need to get something to drink. Everyone should hydrate anyway. We are going to resume after a break of a few minutes. I think over maybe 5 minutes, maybe 10 minutes. We'll see. And we will see each other soon anyway. Enjoy the break and try to move your body. All right, we are back in business. All right, so before the stream, before the break, we added all these connections so that we get the new scheduling tick thing from our task group into the list of sessions. Unfortunately, we see the value remains 0 now. There are a couple of things that can go wrong here, but the most likely is that the value does not even get incremented in the Go runtime here. So probably here we were mistaken in understanding that this would be called all the time, and so it's possible that we're looking here at a case where there are multiple functions that execute slices of time on the Go routine. So we are going to add some little amount of printing. And let's verify that this builds properly. Oh, probably needs a thing here. Write takes an unsafe pointer and an int32. I suppose. How does this work again? I don't remember. Oh, I see. All right. And that needs to go to RFT. All right. Yep. And this function is defined in the str override. I think no. Writeair.go. There we go. Oh no. No? Where is this defined? I don't remember. Print string. Or maybe print string is what I need. Print string? It's here. gwrite bytes. See? gwrite is here. Writeair. Oh, I see. Writeair. Let's do this. Let's do this. Off we go. All right, let's build this now. Another mistake. Yeah, of course. Doesn't need to take CRFT here. And then we stop this and say log to this info, something like this. We need to wait until this build process is completed. Let me stop the heating. Off we go. Okay. So that is not great. Our message is not being printed anywhere. Seems. Cockroach data logs stdr.log. It's not printed anywhere. So that is a sign that either the task group CTX is not being defined properly, which might be surprising, or another option is that this function execute is not being called at all, or not frequently. So what does go do? We'll see. Then we have still work. Okay. All right, so that seems more fine runnable. Where is this used? Here? What is this function we're looking at here? Schedule. Oh, schedule. Oh. That sounds better. So execute is a good place to do this increment, but in fact, in the schedule function, we need to do so as well. That explains. So let's do this. And then schedule. That is more promising. Oh, interesting. Save point FM. I don't know what that is, but that's okay. If we're spinning, yes, I agree. Do we need to wake up the P? Maybe not. Do we need to fetch something? Yes. Run Q get find runnable. See, reset spinning. Sched.disable.users get enabled. Oh, interesting. So it's possible to disable the scheduling of a Go routine. Interesting. Okay, anyway. Do we wake it? Okay. And now hands off P to the locked AMs and blocks waiting for a new P. So we can do two things. So either this one or this one, but I think this is the one that we care about. Start locked M. It's here. Release set note wake up stop M. Release P MP then next P note wake up. Yeah, okay, so that's some kind of... I think that's execute is the right place to look into things. And we're going to briefly verify this by having the execute function report the fact that it gets executed. It's going to be a bit verbose. And then we're going to have execute. And then write error. Yeah. So with this little change here, we are expecting a very verbose plastering of that message on standard error all the time, because assumedly, if my understanding is correct, we are calling this execute function all the time. Exactly. See? This is now super verbose. All right, so I got the function right. This is the right one. So we don't even need to continue with this print. The fact that it's called everywhere is correct. So now we have here another situation, which is that our task group is not defined properly. All right, so that's something we can work on. So this call here we're expecting has been set properly, but apparently it is not. And so it's unclear to me what has happened, but it's possible that we are not looking at the right thing. So what is _g_? Is that some kind of global variable? Yeah, I think it is, huh? Let's search for it. There's some... Oh, it's a colon equal. No, so okay, it's defined locally on every call to the execute function. So _g might be the right thing to look at, but then we don't have the task group defined here properly. So that's kind of an issue. So let's see. So I was kind of expecting that the execute call would be done again and again and again on the same Go routine on every call. So let's look at what go does. We have the definition of go. It's in stubs. Okay, so it's in the ISM thing, so that's okay. Go. Yep. We restore this, and then we jump to the program counter. Yeah, okay, that's exactly what we expected. That's a long jump to resume execution in the Go routine. So so we're still in the right place. So we are going to look at this function here to see if we can maybe have a little bit of printing. To do some debugging. So we are going to do print lock, print and lock, print string, go routine, okay, go routine, execute, println, print int, and then int of g.goid. Cool. And we are going to say print string task, and then print hex. And what does print hex do? uint64 of and save dot pointer g dot task group ctx. Off we go. Let's build this. So, interesting. Here we are assuming, I'm going to assume again that I'm getting a big 64. I'm going to get a big verbose printing. And pointer in 64. I think it works like this. We're going to get a big blob of printing, but we're going to check this. Oh, that is interesting. It's a Go ID 0 here everywhere. Oh, that is not great. Why is a Go ID 0? Why is it 0 everywhere? That is not good. Why is it 0 everywhere? Did we not have something about the Go ID? Group ID, Go ID, curg.goid. So GP is the right one. Where's getGDefine? Let's define in assembly. Here. No? Oh, interesting. Func getG. Yeah, so it returns a G. Oh. So in the right function, but we are not seeing our Go ID and we're not seeing our task group CTX here. So let's do this. I'm assuming the Go ID is defined, so fingers crossed. I'm happy for a fast computer. It's still not fast enough, unfortunately, but... So this is not really good, right? If this was working like we expected, then the Go ID here would not be 0 most of the time. We have a Go ID defined in all the Go routines, and why do we not see anything here? That is really surprising. So here we have no output related to our Go routines. So that's actually interesting. So let's make a little test separately from all this. We have here a test directory, test.go. We're going to import runtime, and then we're going to do here runtime.get HID. All right. And now let's run this small program with our customized Go runtime. Right. Compile in cloud. How is it going? Well, to be fair, I'm pretty excited because I just received a delivery for a Dance Dance Revolution mat, a heart platform. And I can't wait to try it out, which will happen a bit later today. Yeah. Yes. 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 I just got distracted. Anyway, go run test.go. Okay, so we have Go ID 1 here. That's brilliant. So it's not 0 for most Go routines. You missed DDR. You were playing a bunch at an arcade before COVID. Yes, it is fun. It's a good workout. I probably will not perform as good today as I used to when I was 24. I am not necessarily looking at it as a way to be a workout. I think that I'm really missing the music and the moving the body in synchronization with the music, which is very pleasant and a very nice way to achieve a meditative state. That's really what it is. And the thing I was explaining earlier is that this discovery I made a month ago is that there is a company in Poland that is manufacturing high quality, affordable hard pads for use at home. And that seemed to be a very decent alternative to arcade pads. So that's what I'm aiming for. All right. So we have here our Go ID retrieved. So that's actually completely fine here. It's just that in the context of our Go scheduler here, very clearly, the Go ID is not being set. And the reason I just realized is simple. _G is the kind of kernel from the Go routine G, and the one we want to schedule is GP. Oh my gosh, I'm so slow. Do we want the ID of G? No, we don't want the one of G. We want the one of GP, the one that's an argument. I was completely missing this completely earlier. That completely explains also what was going on here. And it's possible that as soon as I build this, is going to get all the scheduling noise that I was expecting. And that means I can probably remove the printing. And then the things are going to work better after that. Yeah. That is so much better. All right. Right. Let's build and then rebuild the CockroachDB and then we'll see. Oh, yeah, but we are going to get all the noise from the print here too. So we don't want this anymore. Yeah. No, it works. Haha, no, it works. Ah, that is going to be so great. Hi, Stephen. Cool, cool, cool. All right, so let's stop the server now. Wait for this to finish building. You say build compile in cloud, but I'm not sure that the cloud is going to give me a computer that is as fast as what I have on by my desk. And I have done some research about this. All right. Where did we have our servers here? My CPU, multiple of them, probably. How is it called again? hope this answers. And so we start the server again. And then we start our SQL shell and node sessions. And now we're talking. Look at this. Scheduling ticks. Nice. Ah. Cool. That is very good. So now we have scheduling ticks. And they're increasing over time because this session is actually not idle. And suppose for a second that I had another shell. And then node sessions. I see my scheduling ticks per session separately computed at last. So happy about this. So happy about this. Now, I want to have a proof that the scheduling ticks are collected properly across children Go routines. So how would I do this? Is there a way? I don't remember if the execution of these SQL queries in Cockroach is done using a Go routine. Window mode is disabled. Yeah, it was. Execute. Not go. That's the one I want. Yes, maybe. No. Maybe Jordan, you remember this. Where if we have the SQL execution happening in a Go routine, or if it's in the parent Go routine. So setup flows is not going to make it work, probably. Run. So here, run. Save flows of the event. Setup flows. Flow.run. Planner. Return func. It's some parent Go routine on the gateway. Yeah. But tell me a little bit about the virtual tables. Did you not have an abstraction to run the to invert the control in virtual Go routine virtual table generators? Yeah, here we are. Look at this. All right. So yeah, so I want to have a way to cause computation in the virtual Go routine generator. Something that's big. It has no exit behavior, doesn't it? What do you mean no exit behavior? I see that it will cancel with the context properly, and it will also exit when the worker has an error. That seems fine to me. Oh, panic behavior. Oh, yes, it does not have a panic behavior. That is a problem. All right, let's file this as an issue because it's actually pretty important. All right. Go routine bound for vtable generators does not go through stopper. The code in SQL virtual table.go contains the following. Is it what I want? People are going to complain. It should use the stopper and run an async task instead, or alternatively share the Go routine registration stuff with the stopper to get the cancellation behavior upon server stop. All right, at the very least, it needs a call to log crash.recover on panic. All right, we have error handling, yes. And that is in the executor. Oh, execution. Oh, yeah, let's put it just like this. Execute. I'm familiar with the idea that those projects have changed. Names, there might be new names later, but whatever. So, the usefulness of Scheduling as a CPU diagnostic depends on how predictably the scheduler is able to preempt Go routines. That, Stephen, is a very good question. I'm going to answer that question in 2 phases. Number 1, the current work that you're observing today on the stream is an experiment, and it's research that I'm doing to see how far we are able to leverage custom Go runtime extensions to get additional insights into Go resource usage that we did not have previously. In this particular case today, we don't have any way to separate CPU usage between different SQL sessions or queries. And so even the scheduling ticks are going to be an improvement, a qualitative improvement upon the status quo. The second phase is that my answer is that the primary use case is not to measure CPU usage in total. Like, we're not looking to bill CPU usage to our customers based on this metric, but instead to detect when there is an outlier, when queries are notably more CPU expensive than others. And so my assumption here is that in aggregate, a query session that consumes more scheduling ticks will actually be more CPU hungry than another, even if the scheduling tick metric is not on a hard real-time schedule. So that's the for this current mechanism. Also, finally, another part is that we are currently experimenting with the very first version of that task group extension that we are prototyping. This task group struct here will probably be equipped over time with additional metrics. And so what we can definitely envision for the future is, in addition to scheduling ticks, an actual timestamp counter delta accumulator that would be set at the beginning of a scheduling slice and at the end of the scheduling slice, so that we have actually precise measurements of CPU clock ticks. And of course, we're not on a timeline yet. I mean, all this work here is completely preliminary, but your concern is valid, and we have maybe other things we can do later. Yeah, there is an issue with timestamp counter, which I am not exactly comfortable with, which is that machines nowadays have frequency adjustments, and I don't recall the semantics on the Intel timestamp counter. Either they have a counter that increments independently of the frequencies on each core, but then it is shared across all cores, and then sampling that counter on every core all the time might actually incur additional memory usage and maybe additional contention on CPU circuits. And if it is specific to cores, which I believe is the case on other CPU architectures, I don't remember about ARM, but we should have a look into this, then obviously the values are not comparable across cores, and we need to be very careful about incrementing counters with the values. So I'm vaguely interested in the timestamp counter from the CPU hardware, but there is another thing we can look into, at least on Linux, and that is the get time of day VDSO variable. So every process on Linux gets a shared variable with the kernel that gives the current time in nanoseconds. That can be read from shared memory at a very low cost, and what we can do is use the actual time, so like the clock, so kernel provided clock variable to measure real time as opposed to timestamp counters from the CPU hardware. And that would be more portable, at least on all architectures supported by Linux would be portable. FreeBSD has something like this as well. I don't recall what macOS does about this, but I mean, that's a service that's more and more available anyway. So, of course, all this is for the future. We're going to play with scheduling ticks for the time being. that's going to start getting us somewhere. But I also wanted to add here fix zip panic behavior here. See here. I wanted to find a way to incur some CPU costs in a different Go routine as a SQL layer. So how do we do this? Well, I actually don't know, but we can do gofunc, search for gofunc throughout the code, and see if we have gofunc. Thank you. If we have some additional Go routine somewhere else that we can investigate, that are not from test code. Oh, the outbox. That is fun. All right. Create stats. I like this. Let's see. Create stats. Yeah, that is nice. All right. So creating the stats for a large table is going to happen in a Go routine, and so then start job is going to probably start it in a separate Go routine. Is that also possible? Take job record, await completion. Yeah, okay. So oh, that's the problem. That is a problem because the await completion. Yeah. Oh, that is not great. Yeah. So jobs are being created in Go routines that are not part of the session. So this Go routine is going to be idle most of the time, and I'm not going to see anything from it. So gofunc. Let's save this result and see. Do we have anything else? Internal.go. Yeah, so this one is a bit of a different one. The internal executor is running on its own session. So I changed the run function here to have its own task group. So all the CPU usage incurred by internal executors in this PR is actually separated session. I suppose that's okay. All right. Well, we're going to just take it like this. What is nice is that our session was idle since earlier, and the value did not increase. So I'm going to wait for a few seconds. Oh, let's do this. PG sleep. All right. So 972. That's the other section from the other shell that is completely idle, did not evolve. And here we have 2905, 2513, 2913. So with a sleep of 0, with nothing in between, we got just a bit less of 10 scheduling ticks for that Go routine. So it's not like we don't get any scheduling ticks at all. And if I wait for 1 second, we are getting more scheduling ticks, but they're kind of idle, and that's okay because if the thing is sleeping, we're completely fine with this. And now we are going to do a thing that actually does work. That was not convincing. More. There we go. Let's get ticks here. Let's get ticks here. So we got here 200 scheduling ticks to compute that that thing here. And if I multiply by 10, so when 415 to 691, so that's actually more than 200. That's like 200 and 80, something like this. And you multiply by 10. So that's actually computing something. So here we are actually doing work. And that's pretty nice. So we go from 3800 to 6,500. That is a bit less than 3,000 ticks. So we went from 280 to 2,800, 10 times more. So we multiply the amount of work by 10 in the SQL query, and we get 100 times more scheduling ticks in the metric. Now, I would say that works quite nicely. Cool. Cool. How do we do the next step here? Well, I think that this is the moment where we go and talk about what happens to people. I think it's a moment to make a nice story about the use case and about what we're doing here. So, number one step is actually to commit our changes to this code here. So this doesn't need to exist anymore. This we know is not relevant anymore. This one here we are going to edit. All right. And then here we have a different API. We commit this. Oh, except that the API has a slightly changed. Yep. All right. Then we push those changes to the branch I had created in our fork of the repository. And then we can make a case out of this by typing in some documents, I suppose. How do we do this? We need probably a text editor. Happy to have a text editor here. And so we are going to say, we're going to go to the RFCs. And then type in an RFC thanks to the new RFC template that we have. Why do I not have this? Oh, because the new RFC template is in a separate directory. Okay, let's go and fix that first. Here. All right. Cockroach, docs, RFCs. And then we're going to create a new one. Precise CPU usage.md. And then we import the template from the new thing here. It's called guide. And cockroach RC's template. All right. And then not precise. Well, actually, I'm not happy about the name I just chose for this document, so let's rename it. 2215 per session CPU usage.md. All right. Per session CPU usage metrics draft. It's actually from last week. So what was the date last week? We were the 8th. And we'll see about that at some point. All right. This RFC proposes to use custom extensions to the Go runtime to track CPU usage per SQL session, and in a later stage constrain CPU usage according to CPU usage quota to quota, configurable quota. I don't know exactly how we're going to achieve this, but we have here some without instrumenting the code manually inside CockroachDB. And all right, motivation. Today there is an issue when a SQL session or query is when CPU usage is high. It is very difficult to track down which SQL session or query is responsible for that load. In turn, the difficulty comes from the Go runtime, which does not provide an abstraction to extract metrics per, I would say, and other metrics, as well as other metrics per session, including all Go routine that do work on behalf of a SQL session and without instrumenting. Okay. In a later stage, this work will also enable constraining CPU usage and other resources according to configurable quota. Right. To extract metric per Go routine, per group of Go routines performing work on a related client-defined query. Related work on a common on behalf of a common session. There we go. Technical design. All right. In a nutshell, the proposed change adds new APIs to Go's runtime package and uses these APIs to create a new task group abstraction which captures counters and other control mechanisms shared by a collection of Go routines. Once this API is in place inside Go, we can extend CockroachDB as follows. Whenever a SQL session is created, a new task group is created for its Go routine. Okay. And is inherited automatically by all new Go routines. Indirectly is bound. its and its children go routine. Right? Okay. This SQL execution on other nodes also sets up a task group for a whenever one or more flows are set up on behalf of a query started on a different node. To connect all the flows for that queries under a common separate task group. As the SQL processors advance or complete work, the current metrics of the task group are pushed back to the gateway to update common counters for the session, and then on the gateway, the virtual table CRDB node sessions and other related facilities report for each session or query the data from the task group additional task group. And once these facilities are in place, we can then extend the task group abstractions inside the Go routine. Alright. And we've got here SQL job execution also creates task groups per job, one per job, in a way that can be inspected separately. Yes, CRDB internal.jobs TBD. We can then extend abstractions as the Go runtime with a per group configurable maximum value such that an exception or other control mechanism is issued whenever the Go runtime encounters notices the metric is exceeding the configured budget. And that is going to be a later improvement, later benefits. Okay, resource control. It's going to be a later benefit. All right. All the things here that are part of the discussion we are going to talk about. Rational and alternatives. The main alternative for the approach taken here is to manually instrument every single entry point in Go where CPU time or memory usage can be incurred. This has been attempted in the past and was largely unsuccessful. All right, explain to someone else. Check and resolve questions. All right, so here we have a couple. How to ensure that CockroachDB can build and run with a standard Go distribution not equipped with the proposed API. We accept. What are the build steps to make this possible? That's the resource monitoring benefits would not be available when the custom extension is not used. All right. What else do we have? Do we want to extend the approach here to also capture, measure resource usage incurred by KV level Go routines? I don't know about that. All right. And so there are some drawbacks here. Maintaining a custom runtime extension in the Go project really means creating a new project by Cockroach Labs, which will be responsible for importing all the changes made upstream by the Go team. That will in turn incur working hours and for the unforeseeable future. We can mitigate that risk by setting up a communication forum with the Go team to demonstrate the runtime extensions we are working with and advocate for their inclusion in the official, in the mainstream Go distribution. As follows. All right. By developing the runtime extensions not as a repository fork, but instead as a batch set, and create automation which will automatically detect changes to upstream Go and apply the patches automatically every time a new Go release is made. This is an approach taken by the redact package to override the FMT behavior C. And now we're going to provide a link here. Journal here. Yeah, like this. Here. All right. Okay. This is additional effort, also requiring a skill set that we have not yet been hiring for inside for CockroachDB. All right, technical design. So we're going to talk about this. Go runtime extension. The center of the proposed approach is the definition of a new task group abstraction inside the Go runtime and scheduler, in addition to the existing GMP abstractions. The reader of this RFC is expected to have familiarity with the GMP abstractions already. Refer to the Go team's own documentation and the top of the runtime.proc.go found the top comment in the Go distribution. Did I say this right? Is this indeed the right file? Yes, it is indeed the right file. All right. A task group is a collection of 0 or more Go routines. Each Go routine is associated to exactly one task group. There is a default global common task group defined initially for all Go routines spawned inside the Go row from the main routine. Initial Go routine. All right. Each new Go routine started with the Go keyword inherits the task group of its parent. A runtime.set task group API enables the application Go applications to override the task group of the current Go routine after this has been overridden. All further Go routines spawned from that point inherit the new task group, but all previously spawned Go routines retain their previously defined task group. All right. And then the Go runtime scheduler is aware of the task groups and is able to maintain update and maintain runtime counters and other metrics at the level of the task group, not just the Go routine. All right, so we are going to have instruction. All right. All right. Internal versus external state for task group. Task group is represented at runtime by two different pieces of state inside the Go runtime. Every Go routine. The internal task group struct has a definition known only to the runtime package and cannot be read or changed by Go applications. There are accessors, public, in the runtime package to retrieve the values stored inside the internal. This is a struct used inside the Go scheduler and other runtime subsystems which you see in the future. A public accessor, for example, and now we're going to talk about our get task group get ticks. Retrieves the number of scheduling ticks incurred by the given task group. Alright. This is visible as type runtime.task group as the opaque. This is defined. Alright. It is also the state defined via the main new API set as group outline above. Alright. Separately, for applications that wish to attach additional state to a task group that can be left opaque to the Go runtime, another API is provided. And that's the other one we had separately, and that is this one. And we are going to rename this logical task group. Interesting. And that means maybe that we want our task group to be internal task group. I like this. I like this. Now we are going to commit this in seconds. Okay. All right. And that is this one. All right. Implementation wise, we extend the G struct inside the Go runtime with two fields, task group CTX. For the internal task group and group ID, maybe we are going to call them differently. Task group CTX, task group ID, and where was that defined again? Here, probably here. All right. All right. And test. Both are inherited when creating a new Go routine and set to defaults when a Go routine is created without a parent. They are initialized as follows. Task group setx is set to default task group setx as a default common task group, and the other one is task group ID is set to the Go routine ID. Ensures. Oh, it's actually kind of a bummer. We probably don't want this. It's kind of odd. We probably are looking at two different concepts here. This default may change, ensure. All right. All right. These defaults are not too important, interesting, since we are focusing, we will focus on overriding the task group for every time we create a new SQL session or job. We will ensure that the task group is overridden. All right. Cool. These IDs can then be used in application code to serve as key in a Go map. Or other similar structure. To attach additional state to a task group. Example, valuable additions. Task group label as a string. And then what else did we ensure we could have looked? SQL statement AST, or maybe some other aspects. Current SQL session. What else we can look at for a task group? Owner or user, and application name. All these additional fields are going to make it easier to understand who or what is responsible for resource usage. All right. Cool. All right. Tracks metrics. So, the internal task group struct will be responsible exclusively to track metrics that cannot be tracked by application code or not effectively. Examples. CPU usage, current total RAM usage, number of discrete heap allocations, and the rest is to be determined. Logical task group. All right. Can be used to attach state identification labels or descriptions. ID. Variable attachments. All right. Cool. All right. Tracked state. Example. Go scheduler is preemptive and allocates and runs CPU slices in segments of time called CPU called ticks, or just ticks. The specific length of a tick is variable, but for CPU heavy loads, but is bounded to a maximum, which is quite small, less than 1. There are more than 10 per second. TBD how much precisely. In time. For CPU heavy loads, every tick tends to use its fully allowable length before control is switched over to a different coroutine to ensure fair scheduling. All right. Context. We want to measure, in order to estimate CPU usage for different SQL queries and sessions, and generally identify which SQL session or query is responsible for peaks in CPU. Probably plural here. CPU usage. We need to collect stats about CPU's scheduler ticks. However, we cannot or do not want to do so. Lee per go routine since a single SQL session or query may be served by many go routines over time. Instead, we wish to collect this metric across all go routines that participate in a SQL query or session. Alright, for this we can use the new task group abstraction. The RC proposes to extend the internal task group struct with a new skeptics field incremented upon every scheduler. tick for the current task group. Example div to add this increment. Now we are going to look at what has been done here. Skeptic, where was it? Skeptic, here. In runtime.proc.go. Oops, not this. Ta-da-da. Ta-dam. All right. All right. Then we can retrieve the scheduling disks for a given task group. Access. In runtime task group.go. All right. And then we can connect this inside SQL on executor runtime.set task group. In con executor.go. All right, run ta-da-da, ta-dam, ta-dam, tam-tam. And then in task group. Okay. Come on. Off we go. Yay. Yeah. Yeah. And then CRDB internal. And then to make it observable, for SQL DBAs in CRDB internal.go. All right. All right. Let's untabify all this to make it clearer. Cool. Example usage. Thanks. Oh, cool. This shows two distinct SQL sessions. There are 2 interactive terminal connected, running a SQL shell connected to this node. The get_ticks column reports that one session has used 972 ticks and the other has used 5 ticks. The value of get_ticks can be confirmed to increase in relation to actual CPU usage. We can compare how the ticks are incremented for several operations. And so here we have operation tick increment. And then that's not going to be very important. What we have is PG sleep. Approximately 20. 1. Also 20. Sleeping time does not incur CPU usage. And then we have the generate series with just 10. It was about 2080. Let's bring all this under quotes. 28. 10 times more. There we go. All right. All right. As this confirms, idle sessions don't increase their get_ticks, whereas busy sessions incremented in proportion to the work actually done. And the goal changes outlined above do not include the aggregation of get_ticks across multiple nodes when queries are distributed. We need to think further about how to reason about CPU usage on multiple nodes and whether we even want this to be aggregated, or whether we want the CPU ticks to be presented side by side for separate nodes. Off we go. So that's a real thing. That is a real thing. And so, yeah, we're going to have here a preliminary version of the proposed Go runtime changes is available in this branch. That is here, and then we need to have a link here. It says commits. There we go. And an example application to measure CPU scheduling ticks. Actually, inside separately for each SQL session is available here, and we probably need to actually make a commit for this. So let's go through the motions of updating this code here. So first, we want to verify that the renaming address affected is still enabling this to compile. No, I made a mistake. Task group. Yeah. Task group. All right. Where was this defined? I don't remember in which file. Runtime 2. Here. And that was group ID. And that will build, I think. Yeah, that seems to build. Let's update our code here. Internal here. Set task group, set internal task group here. And let's verify this builds. Oh, I made a mistake in the spelling of answer gateway. And that is plurals. All right. Yep. Task group. All right. Cool. That seems to build, so we're going to create a PR and some branch name. And so we're going to call it SQL, use the task group, experimental, use go runtime task groups to measures CPU usage per session. This uses the experimental task group API C related RC to measure CPU usage separately per SQL session. Note that this implementation does not yet collect CPU usage for distributed on other nodes. When a query or session and a session runs distributed queries. All right. Now we can push this. Oh, yeah, we actually want to mention the experimental task group API is available in this branch, in this custom branch of the Go runtime. There we go. Right. So this is going to become a PR that is going to be draft, of course. And we are going to make another PR from the master branch for the RFC, which is a separate discussion. Yep. All right. All right. Now we have this. It's going to be a draft PR. Ta-da. All right. Cool. All right. Not just measurements. And so sample metrics, heap usage. This is a bit more complicated because under normal circumstances the Go heap allocator shares small object allocations across multiple data types and Go routines. It would, okay. The basic concept here is to force the Go heap allocator to use different heaps for different task groups. To get right, to achieve this, we change the heap allocator structures to attach a task group to pages, blocks of system memory that are considered to be a unit of system memory that are used to carve heap allocations from. When a heap allocation is performed, the RAM usage counter on the task group is incremented. When the GC liberates all the allocations on the page or block, it decreases the task group's RAM usage by the size of the page. A bit more because to get right, because Go also we probably want to avoid fragmentation for small objects that are only allocated once per SQL session. How to deal with those? There are multiple schemes we can envision, and that is separate the abstraction of task group into sub containers for heap usage, such that the small allocations are built against the common or default task group, while large allocations remain built per task group. This can be considered acceptable if we have confidence that the number of small allocations inside each SQL session or query remains small. Most problematic. Heap allocations are incurred by larger allocations. Problematic heap usage is incurred by large allocations. And the other one we can envision here is to track the task group for every object inside the page, or for groups of objects of the same type. Slices. This will yield more precise and complete heap usage metrics, but incur higher RAM usage overall due to the additional task group tracking. All right. Which scheme to use needs to be guided by further experiments. So it's probable that we will do something about this on stream one of the coming weeks. All right, now we have here our RFC, and we're going to commit this. Resource metrics. Off we go. And we are going to have Nathan, Peter, Ben, and Tobias, because these are the people who have expressed some interest in looking at this. All right. And here we are. All right, so a summary of today. We have polished a little bit our API from last time into something that other people can look at it. And we have further created a RFC, a small RFC, to document the idea and the proposal, so that other people can look at the thing from a more holistic perspective. And we confirmed experimentally in the SQL shells that it actually works. So that's, I think, the most pleasant outcome here, that we have something that we didn't have before, and that we could not get without a extension to the Go runtime. So yeah, I think this is pretty successful, and I'm looking forward to the next iterations where we will do more of this kind of work, and perhaps have a foray into more precise CPU time measurements using actual time or something more clever, and do the work for the heap allocations, because that is also probably the highest priority work that needs to happen right now. Yeah. Well, as usual, if you have comments, feel free to add them on the stream, on the YouTube video. I will be happy to comment. And thank you for attending. Thank you for joining. And I'm going to wish you a very happy week, and hoping to see you again next time. Enjoy your week, and goodbye.